Hello everyone, welcome back. In this video, we are going to start talking about reaction thermodynamics. And you can find this material in chapter 12.3 in your textbook. Okay, so we've mentioned this before, and then we promptly left it. So we talked about exothermic and endothermic reactions. Well, processes. And now we're going to apply this to reactions. So an exothermic reaction is one that gives heat to the surroundings. So the energy of the system decreases and the energy of the surroundings increases. In these exothermic reactions, delta H is less than 0. Now, the opposite of an exothermic reaction is an endothermic reaction. In these reactions, the reaction absorbs heat from the surroundings, and so the energy of the system increases and the energy of the surroundings decreases. And in this case, the enthalpy, the delta H, is greater than 0. So let's talk about this reaction enthalpy, this delta H. We give it the term delta H of reaction M. And remember, this M tells us that we are talking about the system. And so because we're working with a delta, we can think of this as equal to the enthalpy of the products within the system minus the enthalpy of the reactants. So we're really talking about the final state minus the initial state. So if we were given the problem that water decomposes into oxygen and hydrogen gas, and we wanted to find the delta H of this reaction, we'd start trying to think about what would we need to know. Well, we know that H is a function of T and P, and so we'd need to know temperatures and pressures. We also know that the phase, so solid, liquid, or gas, is important in figuring out the energy or the enthalpy of these species. So we'd need to know solids, liquids, gases. And we need to know the balanced chemical reaction because we'd have to know the moles and the atoms involved to be able to figure out what is changing. Now, what we do not need to know is the history of the reactants and products because enthalpy is a state function. So it doesn't matter how this water turned into oxygen and hydrogen gases and the process that it took. It just matters that it did. And so as long as we know the ending state and the initial state, we can figure out this delta H, this enthalpy of reaction. So now comes Hess's law. So oftentimes when we work with these reactions, they don't just go from reactants to products directly along this direct path. You learned in organic chemistry how there are intermediates of reactions. So remember the SN2 reaction where there is an attack of the nucleophile creating this intermediate of that 4-membered species, and then the leaving group leaves. With delta H, we don't have to know anything about that intermediate. We can instead go straight from reactants to products because delta H is a state function. Now, if we wanted to know something about the work involved, then we would have to take into account the intermediates because remember that work is not a state function. Okay, so Hess's law. If I wanted to find the enthalpy of reaction for this top reaction, the antimony plus the chloride goes to form antimony chloride, and I wanted to find the delta H of that reaction. I am given in the problem the delta H of two different reactions. There's this reaction of antimony and chloride going to antimony trichloride, and there's this reaction of antimony chloride, antimony pentachloride, 5 chlorides, decomposing into antimony trichloride and chlorine gas. So Hess's law tells me that as long as I can go from the beginning to the end, that it doesn't matter how I get there. And so what we can do is we can manipulate these reactions and these enthalpies that are given so that they can add up to the overall reaction. Now, to do this, what I like to do is I like to start with figuring out where my reactants are. So I need 2 antimonies solids as a reactant. That is here. And I need 5 chlorine gases. And so my chlorine gas exists here and it exists here. So the first thing that I see that I am going to have to do is I am going to have to flip this reaction. And that is because the Cl2 is on the wrong side. In my overall reaction, my Cl2 is a reactant, and in the second reaction, the Cl2 is on the products. And so to flip the reaction, that is going to be the same thing as multiplying the reaction by -1. Now, the next thing that I want to look at are my products. And so for my products, I want to find, oops, that's a bad color. Sorry, guys. Let's get you a lighter color. I want to find the SbCl5s. And so there is an SbCl5 here, and that is the only spot for it. And now, notice how the SbCl5 here is a reactant and is a product here, but I'm already flipping this reaction, so I should be good. Now comes for these coefficients. So I'm trying to make 2 of these guys, and right now I only have 1. So I am also going to multiply this reaction by 2. So now let's just rewrite and figure out what we have. So I have 2 antimony solid plus 3 Cl2 gas goes to form 2 antimony Cl3 solid, and I have done nothing to this equation and this reaction, and so my delta H is still negative 764.4 kJs per mole. Now, for this reaction, I'm going to flip it and multiply by 2. And so this means that I have 2 SbCl3 solid plus 2Cl2 gas goes to form 2SbCl5 liquid. Now, the delta H is going to be equal to a -2 times this 58.0 kilojoules per mole, because that whatever I do to the reaction, I have to also do to the delta H value. So now, if I add these reactions together, I get 2 antimony solid plus 3Cl2 gas plus 2SbCl3 solid plus 2Cl2 gas goes to form 2SbCl3 solid plus 2SbCl5 gas. And I'm going to worry about the delta H's in a minute. Now, let's simplify. Is there anything, I'm going to look for anything that is both on the products and the reactants. And so that is going to be this antimony trichloride. And so that means that these cancel out. The other thing that I see is that I have Cl2 gas and Cl2 gas, which means that I can combine those. And so this gives me 2 Sb solids plus 5 Cl2 gas goes to form 2 SbCl5 liquid. I changed that. Liquid. That is our overall reaction that we were looking for. And so the delta H is going to be equal to the sum of these delta H's. So this is it written out. See that my delta H reaction of 1 minus 2 times my delta H of reaction of 2 is going to be equal to this negative 880.4, and that is the delta H of my overall reaction. Now, as you do these, you are most likely going to go a lot faster and skip a lot of steps. I know you did some of these in Gen Chem, so you might be a little bit rusty, but they'll come back to you. They just take a little practice. Okay, so why can we do this, and what are we doing? In this reaction, really what we are doing is this is just like the sort of cycle of delta H diagrams that we were working on with changing pressures and temperatures, in that the first step that we're doing, we are going to this intermediate state using delta H of reaction 1, using the red reaction. And then in the second step, we are going from our intermediates to our products, and with that second reaction. And so we know that the overall, the products minus the reactants, is going to be, it doesn't matter what steps that we take. And so we can just add together these two steps and get that overall delta H.